Okay, you guys, so second period we didn't get to go over this. Seventh period we did, or sixth we did. So if you want to fast forward, that's completely fine. Okay. Let pi equal the true proportion of people who catch the flu after getting a flu shot. Pi is equal to 0.5 and the alternate is less than 0.5. So if we take a sample of 100 random people, find beta and the power of the test if the true proportion is 0.45 and alpha equals 0.05. All right, so we drew the curve. This is just a number line, remember, 0.45 and 0.5. You know, on a scale of 0 to positive infinity, this makes sense. 0.5 is where the null hypothesis curve is centered. Since we're claiming the null is 0.5. And the alternate is at 0.45 since we're claiming that value is 0.45. All right, alpha is equal to 0.05. Remember, alpha is associated with the null. This is a lower tailed test, so if we pretend like that blue curve wasn't even here, on the null, alpha would be somewhere in this lower end. We're going to just guesstimate where that's at. We're going to say it's somewhere down here. And that's our alpha value. Our alpha area. Now, the only reason why we use alpha is to find the critical value, because we've already said that this null hypothesis is not true. If we are finding power, we're assuming the alternate is true. But alpha and beta share a critical value, so that's why we're using alpha to get to beta. So they share this critical value right here, that p-value, critical value. And on the opposite side, on the blue curve, is where beta is located. And remember, beta and power make up 100% of the alternate curve. So the alternate curve is the blue one, the null curve is the red one. They are two completely separate curves. One is in front of the other. They just sit at some similar values. That's why we're using them. It says find the critical value using the null and alpha. So using the red curve, I'm going to find out what that critical value is using my z-score formula. So I want to find out what value is this. Okay, well, I'm going to use inverse norm. And I know the area to the left, this alpha value is 0.05. 0 and 1, which gives me a z-score of negative 1.65. So I'm using negative 1.65 equals p minus. Now, notice this says using the null and alpha. So the pi for the null is 0.5. So I'm going to be using 0.5 here. And it's 100. And when you crank this out, p equals 0.418, which makes sense according to our drawing that p is equal to 0.418. So this critical value, or this boundary line, is 0.418. Now, I am done with that red curve. I do not need this red curve anymore at all whatsoever. Now, I am just using the blue curve because it says right here, find beta using the critical value and the alternate. So now I'm only dealing with the blue curve. And I want to find beta. That's what it tells me. Find beta. Well, beta is that green area over here. Beta. Okay. And I'm just going to write a probability statement. Beta is the probability of p, any p value, being greater than that 0.418. And remember, this is when I'm using pi as 0.45 since I'm centered at the alternate because I'm assuming the alternate is true. So basically, we just use the null and alpha to get the critical value, and then we throw it away because we've already said if we're finding power in beta, we know we don't consider this to be true. We consider only the alternate to be true. So I'm just going to use normal CDF like normal. Normal CDF, got a lower bound of 0.418, an upper bound is something big, a mean of 0.45, and standard deviation is 0.45 times 0.55 over 100. And I should get out 0.742. This means there's a 74.2% chance of making a type 2 error. Remember, power plus beta equals 1. So 1 minus 0.742 equals 0.258. That's my probability of power. So there's a 25.8% chance of making a correct decision. Which means choosing the alternate if the alternate is true. So this is a very weak test because if the alternate is true, we're only going to choose it 25% of the time, and we are going to make a mistake probably more. So technically, in a real life sense, if you wanted to increase the power, what would you have to do? Well, you would have to do one of these things, which would probably be increase the sample size. Okay, let's move to the next example. This is now numeric data. Above we were dealing with categorical, and now we're using numeric. Let mu equal the true mean number of pets adopted in December from the local shelter. Okay, the null is that mu equals 10. The alternate is that it's actually greater. If we take a random sample of 50 December records, find beta and power of the test if the true mean is 13 with a standard deviation of 1.3 and alpha is equal to 0.10. Okay, so here we go. We're going to draw a number line. Okay, we've got the null centered at 10. Let's pretend that's here. And we've got the alternate centered at 13. And literally, you can pretend this is a number line. Right? Here's my null curve and my alternate. All right, so we're going to look at the null curve first. Alpha is equal to 0.10, and this is an upper tailed test. So on the null curve, I don't know where I'm going to kind of guesstimate where this is, but I don't really know where alpha lies exactly, but it's somewhere in this upper tail. This is kind of to help me. Okay, and so I want to find that critical value. So let's do that. Here's my formula. Z equals x bar minus mu over sigma over the root n. This is the true mean with the true standard deviation. So we know sigma, we're using Z. All right. In order to find the z-score for this value, I know this is 10%, so area to the left is 90. Inverse norm, 0.900 and 1, and that z-score value is 1.28. So let's plug it in. 1.28 equals x, I don't know what that is, minus mu. Remember, for this instance, we are merely using the information on the null curve. And then we're going to switch to the alternate. 10 over 1.3 over the square root of 50. And we get out that that x bar is equal to actually, you know what, this isn't an x bar, this is just an x. Sorry. It won't let me erase that for whatever reason. X is equal to 10.235. All right, so where I guesstimated my alpha was here, it's actually somewhere over here. So let's adjust this drawing to scale. 10.235. All right, so here it is. 10.235. So on the null curve, this is all alpha. Big probability of a type 1 error. On the alternate curve now, remember they share this critical value. Beta's on the opposite side of alpha, so there's beta. Okay, and here's the power of the test. On the alternate curve. Okay. So I've used the null curve for what I wanted to, which was to find this 10.235 value, and now I'm done with it because I don't think it's true. I already assume I don't think it's true. I already am assuming the alternate's true. So I'm not using this blue curve ever again. I'm only using the red curve now. I only use this blue curve to give me this 10.235 value, and I already am assuming the alternate's true, so why even consider that blue curve anymore? I don't need it. So now find beta using the critical value and the alternate. Okay, beta is right here, and beta is the probability of an x value being less than 10.235 when we're centered at the alternate, when the mu, oops, not 10, when mu is 13, because we're centered at the alternate of 13. Okay, normal CDF. Normal CDF. I got a lower bound of something big. Upper bound 10.235. Mean is 13, and standard deviation is 1.3. Over square root of 50. Okay. Okay, and this is approximately 0. So the probability of a type 2 error is approximately 0. All right, so what does that mean for power? Well, 1 minus 0 equals 1. So there is approximately a 100% chance of making a correct decision. So this is a really good test, a very strong test. Okay. okay? All right, two things that you need to remember. When you are doing this step, you're looking at the null curve, okay? These are things we already know. You know how to draw this because we've been drawing upper tail and lower tail curves for a long time now, okay? So you're just using this null curve to get this critical value. Once you get that critical value, then you're using it to find the probability of beta and alpha. We don't care about the null because we've already assumed it's false. We assume the alternate is true just by proceeding with this problem, okay? So take your time. I'm going to put a key out for the homework a little bit later tonight. Try a few on your own, and then you can go over it, okay?